Okay, we have introduced the definition of uniformly continuous for a map from a subset of Rn to Rm. That is the definition. Suppose A is a subset of Rn and F is a map from A to another Euclidean space Rm. We said that F is uniformly continuous if on A. It is very crucial to identify where you are talking about the definition of the map. F might be uniformly continuous on A, but not uniformly continuous on another set. Therefore, when it is not clear, you need to identify where you are talking about. Is the A or other sets? Okay. So F is uniformly continuous on A if for any epsilon positive, there exists delta positive such that whenever xy belongs to the domain of definition of f, that is A, and the distance from x to y less than this delta, we will have the distance between the image of these 2 points, fx and fa, less than the epsilon. So this is the definition we introduced last time. So now we'll give you another very useful description of uniformly continuity, which is talk about the property by using sequence. This will be very convenient to apply our important result that any bounded sequence has a convergent subsequence. So using the language of sequence is very convenient. So this is the proposition. F from A to Rm is uniformly continuous if and only if whenever xk and yk are sequence in A and the distance of the xk to yk goes to 0 implies that the distance from fxk to fyk will also goes to 0. So this is the sequential description of uniformly continuity. That's very useful. I believe when you study the single variable calculus, you also has a similar proposition. But for completeness, I will prove this here. We talk about the proof. This is if and only if. Therefore, we need to prove the proposition from 2 directions. Firstly, we prove this only if part. Suppose we know that f is uniformly continuous, and we have 2 sequences xk and yk. The point in the sequence become closer and closer. We want to show that their image also become closer and closer. So this is the part we want to prove. So how to prove this? This is what we know about the sequence xk and yk. And this fxk minus fyk, the norm goes to 0, is what we want to prove. So, so for any epsilon positive, because f is uniformly continuous by uniformly continuity of f, we can find an delta positive such that whenever the distance from x to y is less than delta, of course x and y need to belongs to A, then fx minus fy, the norm of fx minus fy will less than epsilon. Okay, this is our condition on the f uniformly continuous. Then for our sequence xk and yk, because we know that their distance goes to 0, so we see that there exists a capital K, which is a natural number, such that once the index K is not less than capital K, then the distance from xk to yk will less than the delta we obtained from epsilon under the uniformly continuity of f. Okay, this is crucial. We use the delta we found here and applied the convergence of the distance from xk to yk, which goes to 0. Therefore, eventually it will less than delta. But our xk and yk are taken from the domain A, and the distance from xk to yk is less than delta. Now, by the definition of delta, the corresponding image of f at xk and yk will satisfy this proposition, this property, follow from the uniformly continuity of f. So we will get fxk, the distance from fxk minus fyk will less than epsilon. So what we get for any epsilon positive, we find a capital K. Once the index little k greater than capital K, then the distance from fxk to fyk will less than epsilon. This is precisely fxk minus fyk. This is a sequence in Rm which goes to 0. Okay, so this proves the only if part of this proposition. Now we prove the if part. For the if part, we want to prove that f is uniformly continuous under our assumption. So we argue by contradiction. If f is not uniformly continuous, okay, then what we have, f is not uniformly continuous means there exists some epsilon positive such that for any delta positive, for any delta positive, there always exists some point x and y belongs to the domain of definition A, so that although the distance from x to y is less than delta, but the distance from their image between that image fx and fy, this is the distance from between fx and fy. This will not less than epsilon. So this is the opposite side of the uniformly continuity. So not uniformly continuity means this. Okay, for there is some epsilon has this property for any delta. Okay, now because this delta is arbitrary, we can take delta equal 1 over k. Here k running from 1, 2, and so on. Then for this delta, for every delta we have the corresponding x and y. So for delta equals to k, a1 over k, we will have xk and yk belongs to the set A, such that the distance from xk to yk is less than delta, which is 1 over k, but fxk minus fyk, the norm of fxk minus fyk is not less than epsilon. So we obtain what we obtained? We obtained two sequences xk and yk. Both sequences belong to the set A, and the distance from these two sequences goes to 0 because it's less than 1 over k. But the distance between the image fxk minus fyk is always not less than epsilon. So So this sequence satisfies xk minus yk goes to 0, but fxk minus fyk, which is a sequence in Rm, is not goes to 0. Is not going to 0. Okay, this is a contradiction to our assumption. Our assumption is any sequence has this property. They become closer and closer. Their image will also become closer and closer. Okay, but we found if f is not uniformly continuous, we can find two sequences in A which become closer and closer, but their image is not become closer and closer. So this is a contradiction. So this contradiction proves the if part of our proposition. Okay.